Now this is our second lesson in Chapter 3 on exponential and logarithmic functions, and so we're going to look at some of the principal features of their graphs, which you should possibly have covered in Algebra 2 as well. And also we're going to do some work on solving equations as well, when the unknown is the index. So first of all, I ask people to sketch this graph by filling in a table of values. So if you forget what a graph looks like, remember you can always create a few coordinates, plot them, and then you can hopefully sketch the graph. So 2 cubed here is going to be 8, 2 squared is 4, 2 to the power of 1 is 2, 2 to the power of 0, anything to the power of 0 is 1, 2 to the power of negative 1, now the negative exponent, remember, means it's going to turn it into a fraction, so 2 to the power of 1 was 2, so this is going to become 1 over 2, and 2 squared was 4, so negative 2 will be 1 over 4, and so on. Now we could then go ahead and plot those points, and I actually have the graph already drawn here, so you can see that you get this shape here. And also that graph you might have seen in science as well, referred to as exponential growth perhaps. Also if you've seen the graph going the other way, then that can be called exponential decay. And you might have seen that for things like half-lives perhaps, or radioactive decay, or something very similar to that. So this is a graph of 2 to the x, which also I have here. And one of the key features of this is, notice it goes through 1, the reason being, again, anything to the power of 0 is going to be 1. Now you can also look at some similar graphs to see what happens if you use slightly different numbers. So if we choose a bigger number for our base, you can see that the graph is steeper. If I choose a number between 0 and 1, which is this fraction here, then you can see it actually goes the opposite way. And you can actually see that this is a reflection of this in the y-axis. Now you might want to think about why that's actually true as well. So 1/5 we can also write down as 5 to the power of negative 1. Now if we use our rules of exponents here, and we multiply the two exponents together here, then we get 5 to the power of negative x. And this is one of our rules for transformations. If we replace x by negative x, then we get a reflection in the y-axis. Now also a very special type of graph is e to the power of x, which we're going to look at in a later lesson. Now e is just a special number, it's an irrational number like pi, it goes on forever and ever, but it's very close to being 2.71, which is one of the reasons I asked you to draw 2 to the power of x, because it's obviously going to be very similar to that one that you just drew. Also, just as a reminder then, e to the negative x, as we replaced x by negative x, the graph is simply a reflection in the y-axis. Now log graphs, your basic log graph is this here. Now notice this is an asymptote here, so there's no negative values at all. And also notice that it goes through 1 on the x-axis this time. The previous graph noticed it went through 1 on the y-axis. And the reason it goes through 1 is, if you remember from last time, the fourth rule of logs is that log of 1 is 0. And you can see that log to the 5 of x comes down a little shallower. And if we do fractions, then they're going to be reflections in the x-axis this time. So this is our graph of what's called the natural log of x. It's a very specific graph of log x, and we're going to talk about that a little bit later. And this is our graph of e to the x. And what you should notice is, and if you look back at the other graphs as well, is you should have noticed that they're a reflection in y equals x. And that's something that we talked about in AICE 1, and also we talked about in Algebra 2 as well. So what we can say that is log x is the inverse of e to the x. And that's actually what we were doing last time when we were switching between those two different equation forms. Now we can actually use these to remind ourselves about domain and range as well. So this is our log graph here. So notice there's no negative values here. So what we can say is domain, and we're talking about x values, greater than 0, can't be equal to 0. If you try log of 0, you're going to find that it's error. Now for the range, you can certainly see this goes downwards forever and ever. This goes up, and it doesn't look like it's going to come back again. It looks like it's going to start actually turning around. It looks like it's not going to carry on forever. It actually does carry on forever. So this one's actually all real numbers. Or you could say negative infinity to infinity as well as another possibility. Now the domain for this one, you can see that this is perfectly good. This carries on forever in this direction and also in this direction. So all real numbers. And our range, you can see that it doesn't go below the x-axis. So we know that the range is going to be y is, oops, can't have the equal to, there's an asymptote there, y is equal to 0. Greater than 0. Now another key thing about inverses is the domain on one becomes the range on the other. and the range on the first one becomes the domain on the second one. So you can see here how we've got real numbers and real numbers, greater than 0 and greater than 0. The only thing I changed is range is y and domain is x. So another property that's quite useful to review an earlier chapter from AICE 1. Now we can also use this to review our work on transformations of graphs as well. So this one says, what is the equation of the graph moved up 2 places? So that's a vertical translation. So what we need to do is just simply add 2 to the end of the equation. Now notice this isn't the log of x plus 2 though. You work out the log of x and then you add on 2. So you don't need to put parentheses around here, but sometimes that avoids us confusion. 2 places moved to the left. So this is a horizontal translation. And when we do this one, we've got to remember to do the opposite of what it said. So left 2, you would think it would be negative 2. Actually, it's x plus 2. Similarly, when we do this one, 3 places to the right, you would think that that would be plus 3, but you've got to remember to do the opposite. So it actually becomes negative 3. Moving down 4 places, that's very similar to this one. So that's just going to be the log of x minus 4. E, what is this equation reflected over the x-axis? So that's one where we flip the graph, so that just becomes negative what we started with. Reflected over the y-axis, this is one that most people forget. This is one where you replace x by negative x, so it would be y equals the log of negative x. Now we can then try extending this. You might want to pause the video at this point and actually try answering a few of these questions, and then check back just to see if you can see what actually happened here. Now notice on our original graph, we went through the point 1, 0. So for this one here, what I've actually done is I've got x minus 2 plus 1. Now we know the plus 1 moves it up 1 place. And x minus 2 in parentheses means we move it 2 places to the right. And then you can see where this graph actually comes from now. So it's the same graph, I just moved it across 2 to the right and 1 up. Now taking this graph, what happens if we move it up 2 places? So in other words, it's this, and I've got to add 2 onto the end. So if I simplify this then, plus 1 and plus 2 gives me plus 3. Now if I move it 2 places to the left, that means I've got to change the thing inside the parentheses. So I already have this. If I want to move it left 2 places, that's like negative 2. But I've got to remember to do the opposite though for this one. So plus 2. And then if I simplify this, you can see that these 2 cancel. So it would just be log of x and then plus 1. Right 3 places, so that's positive 3, but I've got to remember to do the opposite, so that would be negative 3. So I got x minus 2, but now I've also got to take away 3. The original question says plus 1 as well. And then if I simplify this, I'll get the log of x minus 5 plus 1. Move down 4 places. I'll get rid of that because that's a little confusing. So we've already moved it up 1, we're now going to move it down 4, so subtract 4 at the end here. And if we simplify that, positive 1 take away 4 is negative 3. The equation flipped over the x-axis, so that means it's got to be the negative of that equation. And that will reflect it over. Notice I got negative are in parentheses at the start, so you could also say it's the negative log of x minus 2 take away 1. A lot of people remember to do the negative of the first term, but they forget to do it for the whole thing. For the second one, reflected over the y-axis, that means we replace x by negative x, so it would just be the log of negative x minus 2 plus 1. So quite a simple one for that one. Same idea with e to the x, and this one I've already got prepared actually. So if we move this up 2 places, we should know that's going to be plus 2 at the end. Left 2 places, so x we're going to replace by x plus 2, and we're going to do the opposite. And you might want to put parentheses around it, but you don't have to. Right 3 places, if you would think it'd be plus 3, we're going to do the opposite, so negative 3. So e to the power of x minus 3. Oops, that's supposed to say 3. Move down 4 places, so this one, take away 4. What is the equation of this graph reflected over the x-axis? So that's just going to be the negative of whatever it was, so negative e to the x. And reflected over the y-axis means we replace x by negative x. So e to the power of negative x. And same idea for this one. You have to think a little bit more while you're doing this one, so you might want to pause the video for this one. and then here were the answers for this one, so you can check to see that you understood those first ones. So just a good review of some of the work you've done on transformations, but relating it to the graphs that you now need to be familiar with of the exponential function and also the log function. Now our other objective today was to be able to solve exponential equations where the variable is the unknown. Now sometimes people can do these just by looking at them. That doesn't always work, so we're going to look at something a little bit more formal. Whoops. One thing we should try and do is try and do these by hand. See if there's a connection between 8 and 16. Can we write them as a number to some power? And in this case we clearly can. They're both 2 to the power of something. And then we can go ahead and simplify this. So if we have power to a power, that means we multiply the 2 powers together. And then when we come to solve this equation, we can now just say if the base is the same, and that means that the exponents must be the same. So 3x must equal 4, and therefore x equals 4/3. And then you can check, is 8 to the power of 4/3 16? Now actually you should already know that that is true, because this actually means the power of 4/3 means you do a cube root, and then you do to the power of 4. And the cube root of 8 is 2, and 2 to the power of 4 is 16. So 27 and 9, I recognise 9 as 3 squared, and 27 is 3 cubed, so I can do a similar thing. Power to a power here, go ahead and multiply these. Now the bases are the same, we can now say the exponents are the same, so 3x equals 2, and x equals 2/3. Check, power of 2/3 means we do a cube root and then squared, so the cube root of 27 is 3, and if we square it we get 9. Our last one looks a more complicated because we've got a fraction in here. These are both 2 to the power of something. 32 is 2 to the power of 5, so 1 over 32 must be 2 to the power of negative 5. Power to a power will multiply, set the exponents equal to each other, and then go ahead and solve. X to the power of negative 5 over 2. We could check that answer as well. The 2 tells us, on the bottom we're going to do a square root, and the 5 tells you you're going to do to the power of 5. So the square root of 4 is 2, 2 to the power of 5 is 32, and then the negative tells us we're going to flip it and make it 1 over 32. So indeed that would be the correct answer. Now those same questions I've just asked you, another way they could actually ask you that question is, what is log of 8 to 16? Because what you'd actually say is like last lesson, left, right, middle, 8 to the power of something is 16. So just another way they could actually ask that question. They could ask you to solve an exponential equation, or they could ask you to solve a log equation, and essentially those two things are the same. However, it's easier to solve an exponential equation, which is why we try and change the form of that to go ahead and answer that. That should be all the material you need for you to be able to go ahead and do the assignments that are posted in School Fusion for this section.